Let's talk about the magnetic force. Now, you are probably already familiar with the fact that magnets have a north pole and a south pole. And you probably already know that the north pole of a magnet is attracted to the south pole of another magnet. So if we put two magnets here like this, these two magnets, there's going to be an attraction between them. They're attracted to each other. As opposed to if I had a magnet here and I put another magnet like this, these two magnets would repel each other because like poles repel each other. So opposite poles of a magnet attract each other, like poles of a magnet repel each other. So I'm guessing you already knew that. Equally, now this is pretty straightforward, and there's another straightforward case involving magnetic forces about when things are attracted or repel each other, and that deals with currents. So if we're dealing with currents, so let's say I have a current, I'll call this I1, it's going up. Here's I2, it's going up. They're both going the same direction, then they attract each other. Okay. So when you're talking about currents, if they're the same direction, they attract each other. And if they're opposite directions, so if I draw two other currents, say down here, these ones are going opposite directions. This is I3 and I4. Okay. And currents that are going opposite directions, magnetically speaking, they repel each other. The magnetic force that each exerts on the other causes them to repel each other. Okay. So those are pretty straightforward. Opposite poles, when you're talking about magnetism, opposite magnetic poles attract each other, like magnetic poles repel each other. Currents that are in the same direction attract each other, currents in opposite directions repel each other. Okay. But now let's talk about the force on a charged particle due to the magnetic force on a charged particle. So here, let's say we've got this positive charge, and it's going to go to the right. And let's say there is a magnetic field acting on it, or I should say it's immersed in a magnetic field. Okay? And I'll say that magnetic field is going up. So how do I get the direction of the force on this particle? Well, you need to use what is referred to as a right-hand rule, called the right-hand rule, of course, because we're going to use the right hand. And the way you want to do this is you start with your index finger, okay, and you want to point your index finger in the direction of the velocity. So in this case, the velocity is pointing to the right. So there we go. So my index finger is going to the right. Then you want to take your middle finger and point it in the direction of the magnetic field. So the magnetic field is pointing straight up. Right. And then your thumb, you just stick your thumb straight out, and your thumb is pointing in the direction of the magnetic force on that particle. So in this case, my thumb is pointing straight up. And so the magnetic force is straight out of the board. So again, index finger in the direction of the velocity, which I should label, there we go. Middle finger in the direction of the magnetic field. And then the thumb, which you stick straight out, is in the direction of the magnetic force. So this is the right-hand rule for figuring out the force on a charged particle. Now, a couple things I want to point out here about this. By the way, some people, instead of doing individual fingers, they like to just stick their whole hand in the direction of the velocity and then bend all their fingers in the direction of the magnetic field. Some people prefer to do that. That's totally fine. But regardless of which method you're using, and in both methods, the thumb represents the force, regardless of which method, you need to recognize a few limits. First of all, so let's go back to where we're using the individual fingers. For those of you that are more flexible than I am, you can't stick your middle finger this direction. It can't go this direction. It can't go backwards. Okay. If I'm doing my whole hand, I'm not allowed to bend my fingers back. Okay. We start here and you only bend this way. And notice the range of motion. If we're starting here, whether I'm using the whole, all the fingers or just the middle finger. It can start here, which is essentially be 0 degrees, and can go all the way to 180. We don't count that extra bend of our last knuckle to get more than 180. It's from 0 to 180. Okay. And the thumb always sticks straight out. And of course the thumb always sticks straight out because the magnetic force is always perpendicular to both the field and the velocity. So this is the right-hand rule to allow you to figure out the force. Now, I want to point out that the right-hand rule works for positive charges. Okay. If you have a negative charge, so let's in fact just change this to a negative here. So if I change this to a negative, okay, there's two ways to get it. You can use the right-hand rule, go through everything. When you get your force, you take the exact opposite direction. So the exact opposite direction would be into the board, so I just put an X there. There we go. Or for negative charges, you can use the left-hand rule. Now for the left-hand rule, it works the same as the right-hand rule, but of course you're using your left hand. So in this case, you point your index finger in the direction of the velocity. Got to point your middle finger in the direction of the magnetic field. Now notice, of course, right now, I can't do it. Can't point my middle finger in the direction of the magnetic field. So what do I have to do? I have to rotate my hand like so until I can point my middle finger straight up. There we go. The index finger is now in the direction of velocity, middle finger is pointing straight up, and you can't see it very well. There we go, that's about the best I can do, but you can see the thumb is pointing straight down, which is the direction of the magnetic force. So that's the right-hand rule for charged particles. Now let's talk about currents, how to get the force on a current, not because of another current, but just because it's immersed in a magnetic field. It also uses a right-hand rule. So I'll just keep the magnetic field going that way, and I'm going to do the current. This time I'll do the current coming out. So now the current is coming straight out. What's the direction of the magnetic force on the current? Okay, well, it's the right-hand rule still, and the middle finger is still the magnetic field, the thumb is still the force, but now this, instead of being the velocity, it's the current. So that means I have to point my index finger straight up, because the current is straight up. Middle finger has to point straight up. Well, let me do this again. The index finger is pointing straight at the camera, which is the direction of the current here. My middle finger is pointing up, so this would be to the top of your screen, same direction as the magnetic field. And then the thumb, stick the thumb straight out. It's going to be perpendicular to both of these, okay? And it's pointing to the left. So that means the magnetic force is to the left. Now with charges, we have to worry about positive charges and negative charges. We don't have that issue with currents. So there's no other situation. There's no left-hand rule. There's only the right-hand rule when you're talking about currents. Couple things I need to point out in the formula. It doesn't matter if you're doing it for the charge or if you're doing it for a current. In both cases, we've got this sine of theta. So if theta is 0 or 180, then of course the sine of 0 is 0, the sine of 180 is 0. So in both of those situations, the magnetic force is 0. And here in this formula, the angle is between the velocity and the magnetic field. Here the angle is between the direction of the current and the magnetic field. Okay, that's what the angles are. Now, why am I mentioning all this? Because when you're doing the right-hand rule, so for example, let me change this around. Let's say instead my current was going up. Okay, that's the direction of my current. All right, great. So I do the right-hand rule. You stick your index finger in the direction of the current, then the middle finger's in the direction of the magnetic field, thumb sticks out, and it looks like the force is up. No, the force is zero. You need to recognize that if they are parallel or anti-parallel, that there's not going to be a force. That goes for both in the charge case and in the current case. You need to recognize that. The right-hand rule is not going to tell you that. You need to know it ahead of time. I want to do one more example just because you need to see some examples, and I can't do every single possibility, but I want to do one more just to help you understand how the right-hand rule works. So let's do one more. We'll do a positive charge, and this time I'm going to say the positive charge is this way, that's going that way, the velocity is that way, and I'm going to say the magnetic field is down. So once again, I got to stick my index finger in the direction of the velocity. Now my middle finger has to be in the direction of the magnetic field. Notice right now, it's not. It doesn't matter. The range that I'm allowed, which is from 0 to 180, I can't get it to point in the direction of the magnetic field. I have to rotate my whole hand. Okay? In order to get, so I can point my middle finger in the direction of the magnetic field. I also want you to notice that the angle between the velocity and the magnetic field is not 90. It doesn't have to be 90. The only thing that has to be 90 is the angle between the force and the field, and then also the force and the velocity. Or if you're talking about currents, then the force and the direction of the current. But the direction between the angle between the magnetic field and the velocity doesn't have to be 90. The angle between the magnetic field and the current doesn't have to be 90. It can be any angle. But in this case, so the velocity is that way, the current's going down, so I need to rotate my hand so I can bend my middle finger so it's roughly pointing down. So hopefully you can see it's pointing down to the bottom of your screen, and then there's my thumb. I stick my thumb straight out. It's going into my board here. So into your screen. So that means, oops, this is force. The force is going into the screen like that. It takes some practice with the right-hand rule. That's why there's the homework. Certainly, if you're having difficulties, reach out to myself or whomever for some assistance.